So now we come to the next part of the story, and it's to look at the collision zone. This is the collision zone here. It's at the north end of the Himalayan series. We're now getting familiar with these, the Lesser Himalayan, Greater Himalayan, Tethyan Himalayan series. We've looked at them all. But now, what happened where you had this collision? Well, we have to go back to before the collision, which was at 50 million years ago. That's just in the early Eocene. And think about what was happening before. So in that collision zone, which is a zone about 10 kilometers wide, you've got rocks of an age from Triassic right through to late Cretaceous, even into the Paleocene. And they consist of volcanics, of ophiolites, and a whole suite of basic and ultra-basic rocks, which all have oceanic affinities. So what we're seeing in this collision zone is what was within the Tethyan Ocean. And the diagram I showed you before the Tethyan Ocean was a simplification because you had two you had two subduction zones within the ocean, one against the Spong arc and once against the Dras arc. And these volcanic arcs all got compressed together and accreted onto Asia. And so here we are at 56, so this is more or less at the time of the collision. And you can see that some of these oceanic arcs, island arcs, are being forced out southwards on south-verging thrust plains. And so let me tell you about the Mariana Arc. It's the deepest subduction zone anywhere in the world, and it's as deep below sea level as Everest is above sea level. An extraordinary subduction zone creating an island arc. And because I always put north on the right-hand side, I've switched that round so that this is analogous. This Mariana Arc is analogous to one of these arcs, particularly this one here, the Nindam Formation and the Dras Arc. So this is how the Dras Arc formed. Oceanic crust subducted beneath oceanic crust, creating a suite of basic and ultra-basic rocks. One interesting thing was the Spong Arc shot up onto the continent of India and landed on the top of the Tethyan Himalayan series, where you can go and study the ophiolites sitting above Cretaceous limestones. Just to show you some rocks from the suture zone, on the north side of the suture zone, Ganser went and found ophiolites. These basic rocks, when they're weathered, they normally turn to serpentinites, beautiful green serpentinites, and that's what we have here, which he recognized as being evidence of ophiolites. And he defined this major fold and thrust as the great counter thrust, which is mapped out here. This is a different thrust to the ones we've looked at before because it's on the north side of the suture zones. We're on the Asian side of the story now. And here they are, deep green colored rocks, serpentinites, and basic igneous rocks which have weathered badly to these rusty colors. And here, going along the Tsangpo River, which follows the line of the suture zone, you can see these weathered ophiolites. One other thing that you get, which is really interesting along the suture zone, are eclogites. And these are very pretty rocks. These garnets here, we've got, it's all written out here, green omphacite pyroxenes, and you've got glaucophane, blue glaucophane in there. There's a thin section of this eclogite. It weathers black, and it's been down to about 80 kilometers below the surface on a thrust, and then perhaps as a result of slab break-off, which we'll come to later, has come back up to the surface. And so this is a feature. These are ultra-high pressure rocks and are typical of suture zones. So just a few more words about this Asian block, where you have a Ladakh batholith and the Karakoram batholith. They formed in the same way that the rocks are forming today in the Andes. As a result of subduction, this we can imagine as the Tethys Ocean being subducted beneath the Asian continent. And you get andesitic volcanics at the surface, and you get granites at depth. And that's exactly what we have in the Ladakh batholith. And it's similar in the Karakoram batholith. And I think we'll skip all those words. These are some landscapes from the Asian bloc. Dramatic scenery up in Ladakh, in the northern part of India, Tibet just across the border, Bactrian camels, beautiful lake, the largest high-altitude lake in India, and it's an endorheic lake. It means that there's water can't escape. There is no outlet from the lake. And yet, ironically, it's not particularly saline. So now we're going to come back to what happened in the main part of the mountain chain. Because I've taken you on a tour so far, right from the Swalik's in the south to the Asian bloc. I've shown you how this lot came from the south to collide with this in the north. But what happened when the collision took place from 50 million years onwards? Well, we'll call it the Indian fragment because it's a continental fragment that's broken away from Gondwana. On the northern margin of the Indian fragment, you had this passive margin full of sediments which can be as thick as some 20 kilometers of section. And this is what it looked like with the continental shelf, the rise, the slope and the rise. If you do sandbox modeling and you establish some layers of white and blue sand and then squeeze it from the right-hand side, this is what happens. And when you've got 30% closure, you get folds. And when you've got 44% contraction, I should have said, you get thrusts. So the fold breaks and you get a thrust coming up out of the focus point. And that's exactly what you see in the mountain chain. This is a picture taken by Mike Searle in Ladakh, some kilometer high, 1,000 meters, great fold, matching some of the folds that you could see in the sandbox. And now let's look at some of the thrusts that you can see. Well, this is a modeling of thrusts. And the way it works is that firstly you get a break and you get this horse rising up here. We call them horses. The next one, you get a break here, and the second thrust sheet is that. And the third thrust sheet is this one. And in short, the mountain chain is built up of a great stack of thrust sheets, as illustrated in this theoretical model. And this is also a model, but it's based upon the actual rocks and thrusts that you see in the lesser Himalayan series. This is the greater Himalayan series, and this is the Tethyan, but most of this is lesser Himalayan. And here's a model starting off with everything flat, and you get one thrust sheet, another one coming up underneath it, and so on. It's far too much to explain. You just get the general picture that you're stacking up thrust sheets. You're also getting a lot of erosion away. Of what rises up is eroded away. But remember what we said here, that for every 1 meter you put on top, because of isostasy, you've got to put another 7 meters down below. People sometimes say, could Everest be much higher? Might it have been much higher? Well, it's 9 kilometers above the surface, so you have to have 80 kilometers below. There's a limiting point to how thick you can make that root of the mountain chain. Mountain chains are complicated places. And because I always put north on the right, these have been reversed. But this is the Rockies. Look at this great collection of thrusts. And as I say, those drawing these diagrams have been concerned primarily to map out the thrusts. But we should remember there's a deep root underneath both of these mountains, the Rockies and the Cantabrian Mountains in Spain. Now, this collision, it didn't happen gently. It didn't happen gradually over time. It happened episodically. You build up tremendous tension on these thrusts, and eventually that tension gives, and you get an earthquake. You get a movement on the thrust. Now, here's the main Himalayan thrust. This was responsible for the Gorkha earthquake of 2015. The movement was about 1 meter, just 1 meter, enough to shake the whole mountain chain. Well, that's an exaggeration, but the whole of that region of west central Nepal. And it caused some parts of the Himalayas to rise up quite significantly, perhaps 0.5 meter. But actually in some other places you saw the surface decline. And so these movements take place in a very complicated way and episodically and at an interval of about every 800 years. You can work out statistically and from records that there's a sort of periodicity of about 800 years in the Himalayas. That's not a universal rule for other mountains.